Pre-calculus, lesson 2.4 in the calculus textbook. So a little bit of side notes. This is actually the first video I'm recording in the calculus textbook. It's technically only for one student right now, but who knows, maybe I'll use this video in the future. So at this point in the book, we've already progressed past pre-calculus. We've finished pre-calculus. We're doing full-on calculus, as much calculus as I can remember to help you out with anyway. And this lesson on chapter 2.4 is rates of change and tangent lines. I did talk about this briefly during an online class, but I don't think I explained it as well as I could have, and I definitely know I messed up when I was explaining the slopes of normal lines. So when we get to that point, I'll explain the confusion. But let's get going on average rates of change. So something that we should already understand is that an average rate of change is a secant slope. If we remember from geometry, a secant line is a line that passes through a circle, or in this case, we're using it as a curve. So it passes through 2 points of the curve. That's something that we would consider a pretty normal linear slope. So if we take the secant line, that's just a normal rise over run delta y over delta x slope. And what we see here is that the value of the run, or the denominator, would be the distance from left to right. The numerator would be the distance from top to bottom. That's a pretty typical secant slope. We can see it right here. Not too difficult. Pretty easy to figure out. We've been doing that ever since Algebra 1. Sometimes some of you maybe even since pre-algebra. So that's a secant slope. And we're calculating secant slopes on curvy lines based on 2 points on the line, like this one right here. Now, the reason why this matters is because if we don't understand how a secant slopes on a works on a curve, we're going to have a difficult time understanding a tangent slope on a curve. Okay, so if we remember, a tangent slope on a curve is a slope that only passes through 1 point. You know, I'm just going to go straight to the my whiteboards because that makes more sense, right? So the concept of a tangent slope on a curve is closely related to the idea of moving infinitesimal amounts, right? So normally, and the short answer is tangent slopes are really cool because they help us calculate slopes using 1 point. Typically, in order to calculate the slope of a line, you need 2 points, like A and B, right? So we got point A, we got point B, right? We got our delta y, our delta x, those two coordinate points. I'll just go ahead and use the approximations here. We got 0, 3.5, and then it looks like we've got 6. And why did I pick such a large number? 1, 2, 3, 4, 5, 6, 7, 8, 9, 6, 9, right? So we've got two precise coordinate points of about 3.5, 6, 9. And that's how we get the slope of our line, by doing delta y over delta x. Well, tangent slopes, they help us find the slope of a line using only 1 point, 1 and 1 point only. So for example, this tangent, or the secant slope, would be the slope of a curve. Let's say the curve rose like this, right? And the secant slope, actually that was a bad example. I was supposed to curve it the other way. Whatever. So the secant slope is passing through the points A and B, and we're getting a general rate of change over that interval of time, the interval being delta x. Now, how in the world do I calculate a slope using only 1 point, right? So let's say I just pick 1 point on the line right here. That'll be my single point, and I'm going to calculate what's called a tangent slope, right? So tangent being like tangent to a circle, only touches at 1 point on the curve, meaning I've only got 1 point of data to get a slope out of, right? Well, the way we do that is we're going to use the concept of infinitesimals. So I'm going to zoom in super close on this point right here. So I'm going to zoom in on that little box right there. I'm going to use this graph to do it. Okay. So what happens as I've got my curve, actually, yeah. So I've got my curve, going right here, and I've zoomed in on that red point, that red tangent point on the curve, right? Well, in order to figure out this, I'm going to use infinitesimal amounts of shifting either left or right. It doesn't really matter. We'll say we'll shift to the right. Okay, so let's say we're zoomed in super far. The distance from, we'll say the distance from here to here. That's the interval of like 0.01 to 0.02, right? So this whole distance is just 1/100th of a unit, right? So I'm talking about like 1/100th of one of these boxes. That's how zoomed in we are, right? So if I were to shift an infinitesimal amount, you know, say like 3/100ths to the right, right? And I used that for my delta x, right? And if we remember in calculus, logically, if we look at infinitesimal amounts as they relate to limits, that's practically the number to 0. So let's say I'm shifting, well, instead of delta x, the distance will be x, right? So I move this many units to the right. What units? Oh, right. Yeah. So the notation the book uses, we'll call that h units, right? H units. We'll say h is equal to like 0.003, 3,000th of a unit. So incredibly small distance. We're moving that many units to the right, or let's just make it even more ridiculous, right? We'll make it 0.0001. That's how small we're moving to the right. That's how infinitesimally tiny this movement is, right? So if we move to the right, well, then this y value is going to rise, right? I'm not exactly sure what that rise is going to be, though, right? Now, let's look at these x values, right? As I go from my actual f of x point, right? We'll call this the value at x, and then over here, this value that the other infinitesimally small distance is going to be, well, that's going to be the value of x plus this distance of h, right? Because if I'm moving h units to the right, well, this x value is just going to be x plus h, right? This should all start looking really familiar to you guys, especially after coming out of the advanced math book. We saw a lot of functions of f of x plus h, right? The reason why you kept calculating all those functions was to prepare you for this moment, this lesson, this instant right here in calculus. Now, the frustrating thing is your textbook, the one that we're using, they actually, instead of using the letter X, they use the letter A. I'm sticking with the letter X in the example because it's most closely related to what we understand coming from our textbook, and we can kind of start to translate it after that. So I'll go ahead and explain it using the letter X, and then at the end we'll just substitute X for the letter A so we can see how it works in the textbook. All right? So in this case, my delta X, or my slope, right? Because slope is going to be delta Y over delta x, yeah? So my delta x, the distance that x moves, well, that's just going to be the letter h, right? I've already figured that out. So when it comes to calculating my slope, my denominator is just going to be h, right? That's going to be the answer for my slope. Delta x equals h. What about delta y? How do I figure out the value as this point went up to that point, right? Well, if you remember functional notation, as we plug in x values, we get y answers, right? So if I were to calculate f of x at this point, that would give me the y coordinate right here, right? So this distance, or my delta y, being y1 minus y2, right? My y1 would be f of x, okay? So right here I've got f of x. So I'm going to substitute this y1 minus y2. I'm going to put it down here. So now I've got f of x. Okay, great, got it. Now let's talk about how do I get this value right here? Well, this value, that's going to be x plus h, right? So if I was going to calculate the functional value of what this coordinate is, instead of doing f of x, I just do f of x plus h, right? So I'm going to do f of x minus f of x plus h, right? Cool. Now, the funny thing is, if you remember when I'm calculating slopes, I can do whichever direction I want, right? So instead of doing y1 minus y2, let's do y2 minus y1, right? That'll make something that looks a lot more familiar to us, right? I can get away with that because that's how slopes work. It doesn't matter which direction I go as long as I'm consistent, and I don't have to change my denominator because I already know the set value of the denominator. That's the infinitesimally small distance h. Okay, so what I can do in my denominator is if I make it y2 minus y1, I remember y2, well, that's going to be f of x plus h, right? Whatever the answer is to that functional notation, that'll be the value of y. And then I'm subtracting f of x because that's the functional value of whatever that y value is. So now I've just created this incredibly familiar equation, f of x plus h minus f of x all over h. Right? You should memorize. You should have that formula practically memorized from the advanced math textbook, because at the end of almost every single lesson, they were having you solve functional expressions in this exact form. And that's one of the great things about the Saxon book. They brainwash you into understanding stuff that's useful in the future. And that's where this formula comes from. So the value of h is an infinitesimally small amount that you're shifting to the right or left. It doesn't matter if you go right or left, because of this reversal of y1 minus y2 or y2 minus y1, you'll always be able to rewrite it in this form like I just did. So it doesn't matter if you go infinitesimally to the right or infinitesimally to the left, you'll be able to write it out in this function. So what happens though is I still haven't figured out my tangent slope, right? I still haven't figured out the slope of the line as it passes through this point, right? Now, if we remember our initial lesson on limits, right, we can treat infinitesimals or incredibly small numbers as being practically zero, right? So essentially what I do now is I take this formula that I've created for this tangent slope, and instead of calculating it as a functional notation, I'm going to calculate it as a limit. So now I'm going to do the limit as h, remember that infinitesimally small shift that I'm actually moving, approaches 0, because it's practically 0. Okay? Whoops, I dropped my marker cap. So as h approaches practically 0, I can calculate the limit of this function, and then I will then know the tangent slope at this value. Because if you remember the intermediate, what was it? The fundamental theorem of calculus. Wait, no, sorry, not the fundamental theorem of calculus. Hold on, I got to get the right name. Let me pause. Oh, wow, I just remember this book doesn't give it a name. They call it Theorem 1. Theorem 1 in this book, you find it on page 58. Theorem 1 in this book, the main theorem about limits is that if we were to calculate limits of simple polynomial functions, we could just say that f of x is also the same as the limit of x as it approaches that number, right? So if we do the limit as h approaches 0, we can in fact actually find out what this tangent slope is, this red line right here. Right? So if we do the limit as h approaches 0, we have in fact figured out the slope of a line using one and only one point. I just have to know what the value x is, right? If I know what my x is, I can figure out the slope of a line using one and only one point. Pretty cool stuff. So let's do it in practice. Okay, so I'm gonna let's go ahead and do a tough one, right? So that way we can kind of get the idea, and we can link this to some of those difficult problems we had at the end of the advanced math book. So let's go to page 88. We're gonna do problem number 12, right? In the instructions above 12, they say in exercises 9 through 12, at the indicated point, find the slope of the curve, an equation of the tangent, and an equation of the normal. Then draw a graph of the curved tangent line and the normal line in the same square viewing window. Right. So we'll focus mostly on A and B, and then when we get to C, I'll explain what the normal line is and how to draw that. So I'll keep this, I'll maintain this little limit f of x as things approach 0, and I'll grab my other whiteboard. Go ahead and erase this. Don't need it no more. Oh, that was gross. I didn't like that. Don't need it anymore. I tried to shorten the sentence. That was just icky. Okay. Let's see here. Problem number 12. Actually, I'm pretty sure I can do most of this on the back side because I don't need the graph. So they tell me we've got the function, we've got the equation y equals x squared minus 3x minus 1, and we need to evaluate the slope of the curve at the point x equals 0. So essentially what we've got here, we have to rewrite this in functional notation so our brains can wrap around it. F of x is equal to x squared minus 3x minus 1. We're evaluating this limit, we're evaluating this this curve at the point x equals 0. Right, so that's going to be our P1 or our x value. Now we just have to solve our limit as h approaches 0 for that. But before we do that, we need to make sure we are plugging in the f of x plus h and the f of x. All right, so f of x is this. F of x plus h, you guys already know that's going to be a bit difficult. We're going to have to do some work with some polynomials. Okay, so let's plug it in. We'll go ahead. I'll write the numerator in red for some consistency. So let's see here. F of x plus h, well, that is going to equal x plus h squared minus 3 times x plus h minus 1. Right? F of x we can already see up there. If I simplify f of x plus h, which is a great idea, x plus h squared, well, that's going to give me x squared plus 2xh plus h squared minus 3x minus 3h minus 1. Okay, so that's the first half of my numerator for f of x plus h. Now we have to do minus f of x. So then we'll take this and we will I'll just keep it all in red. I'm going to take this value, move it down there. So then we have minus x squared plus 3x. Why did I change the signs? Because the subtraction, this minus sign distributes. Okay, so don't forget about that. And then it becomes plus 1. So let's see. I can cancel some x squareds. Hey, 3x and negative 3x, they cancel. Positive 1, negative 1, they cancel. So now I'm left with just the quadratic. I have h squared plus 2x h minus 3h all over h, right? And this is great because I'm calculating the limit as h approaches 0, and I need to use some algebra to rewrite this. So let's factor h out as the greatest common factor. Go ahead and switch over to a nicer color like blue. So if I rewrite this numerator, now I've got h parentheses h plus 2x minus 3 all over h. That cancels, so now I've got h plus 2x minus 3 as h approaches 0. So as h approaches 0, now the limit is just going to be 2x minus 3. Or since the point is at x equals 0, so if h approaches 0 and x is equal to 0, then the tangent slope is just going to be negative 3, because then I've got 0 plus 2 times 0 minus 3, which means my tangent slope is just equal to negative 3. Kapow. Now let me double check this, make sure that it's right. Yes, that checks out according to L'Hopital. Don't worry, you'll learn about him later. It's my fast way of checking these limits without doing all of this algebra, but for now you guys got to do the grinding of calculating all this algebra. Now that my tangent slope is m equals negative 3, I have found part A. I have found the slope of the curve. Now, what is an equation of the tangent, right? Wait, what? Hold on, let me reread this. An equation of the tangent. Oh, no, I remember. Okay, so the equation of the tangent. So remember, that's why I saved this drawing. So remember, the tangent line is a linear equation. So now when they say equation of the tangent, they want this linear equation, this red line. What's the equation of that red line? Well, I know the slope is 3, and I know the x interval is 0. So I've got a couple pieces of this equation. So I could say that, hey, y equals the slope of negative 3 times the x value of 0 plus b. If only I knew what the y value was at x equals 0. Oh wait, I can figure that out. I just have to calculate f of x. So if I calculate f of x, I get the y value. So if x equals 0, well, 0 squared minus 3 times 0, well, that's 0 minus 0, negative 1. Ah, the y value must be negative 1. So now I've got the interval 0 comma negative 1. I can plug negative 1 into that y. And now I find out that the b is equal to negative 1, which means the equation of my tangent is going to be y is equal to negative 3x minus 1. Okay? Now, that's the equation of my tangent line. What is next? Okay, now they want to find the equation of the normal line. Okay, this is something I did not quite talk about yet. So the normal line is kind of like the radius to the tangent. So if we remember when we talk about circles in geometry, I'll just go ahead and use the back of this. When we talk about circles in geometry, the tangent to a circle is a point that touches the circle at exactly one point, and that one point is also perpendicular to the radius or the diameter that passes through the center of the circle, right? So we just found our tangent line. That's what we found right here. That is y equals negative 3x minus 1. And this is the part that I messed up in class because I was reading the book because I didn't trust myself. Yeah, that was a mistake. So it's just the perpendicular. The normal line is just the perpendicular line, right? That's why we spend so much time finding these in Algebra 1 and Algebra 2, and also in trigonometry class. So the perpendicular line is just going to be the linear equation that is the perpendicular to this. So all I have to do is, I already know this point. This point I solved over here was 0, comma, -1, right? So if this is 0, comma, -1, and I've got to find the normal line, well, I just got to find the perpendicular slope. The perpendicular slope is going to be the negative reciprocal of -3. So the negative reciprocal is positive 1/3. So that's my slope of my perpendicular line. So now I've got y is equal to 1/3 x plus b. I'm going to take these 2 points, plug them in. So now I've got -1 is equal to 1/3 times 0 plus b. Hey, 0 is just going to cancel that out, so b is equal to -1. So now I've got y is equal to 1/3 x minus 1. This is the normal. Right, so now I've got the equation of the normal. Last thing would be to draw a graph of the curve, the tangent line, and the normal line in the same square viewing window. So that's where we're going to use the graph. All right, so we've done all this math. We'll go to the graph of this window. Oh wow, this has turned out to be a long video, but that's okay because you guys made it all the way to calculus, so you can handle this. If I can make it, so can you. So now we need to draw the graph of this. I've got a couple of linear equations that are on the back of these respective boards. So the graph of the normal line, that's pretty easy. I'll just go to -1. Whoops. Let's use a green that works. I'll go to -1. This is my normal line, by the way. And I've got a slope of positive 1/3, so 1/3, 1/3, -1/3. Cool. This is my normal line. This is the normal. Okay, and then I've also got my tangent line, which thankfully I drew over here, which is y equals -3x minus 1. So I'm at -1, a slope of -3x. Well, that's going to be -3 over 1, -3 over 1, over 1 up 3, over 1 up 3. Great. This is my tangent line. This is the tangent. Okay. This is the point on the curve that it crosses. Now the last thing I need to do is I need to graph the original function, which is y equals x squared minus 3x minus 1. To do that, let's just go ahead and use our graphing calculators. Yes, that is allowed. We made it this far. We can use our graphing calculators for graphing things like quadratics. I'm not going to make you complete the square root graph right now. That's ridiculous. Okay, so we've got x squared. I lost the equation. Minus 3x minus 1. All right, let's graph. Hopefully my calculator is on the right mode. Let's see here. Normal, auto, real, degree. Okay, yeah, this should be the right mode. Where's my... what are my window settings set at? I'll make x minimum 10, x max 10, x scale 1, y minimum. Whoops. Oh, -10. That's what. Whoops. Minimum should be -10. Max will be 10. Scale 1, 1. Okay, great. Let's graph. That's much better. All right, cool. So if we, let's change the window. Let's make it a little bit closer. We'll go -5 and +5. After all that work for me to make it 10 and 10. Okay, now let's graph, because I need to see what's going on right down here. All right, so it looks like my curve passes right there in between -1 and 0. Got my curve going that way. It looks like it bottoms out right at right in between -3, -4, maybe right at -3. I don't know, hard to say. Looks like it's right around here and here-ish. That's where my curve bottoms out. And then it turns back up. Whoa. So this is the actual graph of my parabola. All right. And then we can see the tangent line right there if I were to draw better. It's a little off scale because this is zoomed in a lot more and this graph is a little big. But we can see here if I were to draw it perfectly, I'll draw it freehand so that way you guys can see. This will be the last thing and then I'll let you guys go, I promise. So if I draw this freehand, the way I would do it is I'd probably start off by drawing the curve first, right? So I've got my x-axis, so let's go to -1. There's a point on my curve. Then let's see here, 1, 2, 1, 2. Let's see here, 3. Okay, there's the one x-intercept, here's the other x-intercept, and then if I go down -2, -3, it looks like we're right in between here. So it looks like we're right around there. My graph is kind of doing this, right? So there's my parabola, and then from here I can go ahead and graph my tangent lines. So tangent line had this point, it went -3, so 1, 2, 3, 1, and then 1, 2, 3, 1. Okay, right, so my tangent line is right around there, and then we had something like that for the normal, right? So then I could say that's the normal, that's the tangent, and here's f of x. Okay. Wow. Hey, we made it through our first calculus video. If you guys have any questions, let me know on the school website. And yeah, I don't know. Maybe I'll use this in future classes. Not sure. That's it.